convergence rate goes goes with 1 over square root n. Okay, so this was the final message of the Monte Carlo method, that when you do Monte Carlo, you have to run really a lot of samples. And even if you do run a lot of samples, you have to know that you may get a wrong sample from this Gaussian distribution. Okay, so now we see an example how to use this sglib library package. And for that, I created, not only for you, okay, I created this link for a chapter, which is for a book that we have submitted together with Emil Zander and Professor Matisse and another colleague of mine for this publication, for a publication of the book. And it's still not published. And I asked the editors, what shall I do? How could I share this chapter with you? So they told me I can privately share it. So I can send you this. Actually, there are 2 chapters, one about identification methods and one chapter specifically about a nonlinear filter. So I can, and I will send this to Bostian and he can distribute this. I also updated a little bit the end of this presentation that I had last time. So I will also send him the updated presentation. So please check out this link, because under this link you will find all the MATLAB examples that I will present you, and also some more examples that may be really useful if you want to practice or actually really carry out uncertainty quantification or Bayesian inversion on your own. So in this library package, you have these low-level functions like these GenDist functions. It comes from generating distribution. So you have these GenDist functions, and you can create like that any type of distribution which is defined in the statistics folder that I showed you before. You can change the distribution by fixing some moments, for example, to have mean 2 and variance 0.5. You can do this with this function. You can do this in one step that I have here. And then if you created this distribution, then there are many things you can do with it. For example, then you have access to the inverse CDF of the function, with which you can sample from the distribution. And you have access to the probability distribution function and the cumulative distribution function. And you see here these plotted. So these are the low-level functions. There are also higher-level functions that I will show you later on. You can see that there are different distributions like the beta distribution. This is a bounded distribution. And you can also fix the bound of the distribution by saying that when you create a beta distribution, then it will be bounded from -1 to 1. And you can change that by shifting and scaling, but telling to fix the bounds to, I don't know, here 0 and 3. So that the support of the beta distribution, which is something like, let me show you just a minute, which is something like, it depends on the parameters, but oops, sorry, sorry, I don't have to push the button. It's something like that. And it looks like a Gaussian, but it is bounded. So it's a useful distribution actually for engineers who want to use something similar to a Gaussian distribution, but their distribution is actually bounded. You can play these alpha and beta parameters to get skewed. Sorry, it's not so easy to use this. Skewed distribution, not like this, but looks like a Gaussian, but a bit skewed. Okay, good. So beta distribution is a useful distribution, and you also have that available in the library package. Also, you have here the inverse CDF function. You can sample. The sampling is doing the same thing how I use the samples from here. So you can play around with it. You can see examples on this website that I showed you. I'm not going to go in all the details, and you have the plotted two beta distributions here. This is two random variables. You see here the sample points, and you see the probability density function in the two directions. Now, this is the assignment that I wanted to give you. And the assignment is the example that Professor Mattis mentioned you. So the task is that by Monte Carlo method, you should approximate the value of pi. To estimate the value of pi, we will estimate the area of this circle. What we will do, we will throw darts to this table. And throwing darts only means sampling from a uniform distribution. I have two random variables, one in the x direction, one in the y direction. And let's say they are, I don't remember in the example, it's shown, maybe it's from 0 to 1 or a -1 to 1, I don't remember, you have to check. And I have to see how many darts or samples landed inside the circle and how many darts did I sample in total. And the ratio in between these two will give the ratio of the areas of the circle and this square shape. So knowing the ratio, which I can compute, which is here, I can estimate this ratio from the samples by checking how many samples are inside and how many samples are in total. And from this ratio, I can compute the value of pi, which is 4 times this ratio. Now for that, I made a function for you that you can see here and in the next slide. So it's taking an n number, how many samples you want to throw, and the mode, whether you want to use Monte Carlo or quasi-Monte Carlo samples. I will talk about quasi-Monte Carlo later on, though Professor Mattis mentioned you already. And with this method, you can actually compute the value of pi. So this is an assignment you should try. You are not forced to try. No one's going to ask you if you did. But if you need any help, you can ask me any questions. And try it with different number of n's and see how your estimate of pi is changing. And then you will have an idea about the accuracy of the Monte Carlo method. You can also try it with quasi-Monte Carlo, and then you see the difference between the two. And I gave you here another assignment, as you will have, and you already have this slide. I'm not going to read it, but the idea is that you choose a small finite element model and you choose some parameters of it, Q. You decide how many parameters you want to choose. I would start with something like 2 to practice. So let's say there are 2 inputs that are uncertain, and you assign to this uncertain random variable some distribution, and try to check the variance of U and the mean value of U, and try to estimate with Monte Carlo and quasi-Monte Carlo methods. You will find some examples here that will help you, that you will see later on. So this is your task to do if you would like to practice. I think all these theories are very difficult, but once you try to actually do it, you see it's not so complicated. So this is what I would advise you to do. So we are still in the uncertainty quantification part, in the forward problem. And what we saw that if we have some response U and we want to see how the uncertainties of some parameters, let's say the stiffness and the mass is propagating through the solution U, I can compute the mean value with an integral term, and the integral term, so the mean value, I can approximate with a numerical integration. So Monte Carlo you can see it as a numerical integration, where the integration points are the random samples of K and M. Those are the integration points, which I assigned as Q of omega I. And the integration weights are the same for every point. So you just take, if you have M samples, then the weights of the samples will be just simply 1 over N. And then you need to evaluate the response U, or psi, if it's a function of U that you want the mean value of, by taking this response with the different sampled values, computing the solution, multiplying it with its weight, and sum them all up. And then you get an estimate, a Monte Carlo estimate of the mean of the solution. You can do the same thing if you want the variance, then you square this and subtract the mean value, and you can also evaluate that. So this is by the Monte Carlo method. Now I will show you what's, just with one slide, what's the difference between Monte Carlo and quasi-Monte Carlo method, and then I will go to the quadrature rules. Okay, so Monte Carlo method, I'm just throwing samples. This is K, this is M, and I'm throwing samples, and I have to run the solution with those samples. The problem is, as Professor Mattis explained you already, that you can see that there are some regions which stay completely empty, and there are some other places where the number of points is quite scattered. So there are more points here than, for example, here. So what I would like to have is that if I make some shapes like that, if they have the same area, I want them to have more or less equal number of samples. And quasi-Monte Carlo samples are generated from low discrepancy samples, and low discrepancy means this actually, that the number of the samples is proportional to the area that I'm drawing here. So this is what the QMC is supposed to do. They are not completely random. They are not generated in a completely random way. It's a quasi-random way. But you see that then the samples are more distributed. And unfortunately, this type of sample is actually depending on the number of the samples, the convergence. Sorry, it doesn't depend on the number of the samples. They all depend on the number of the samples, but I wanted, I don't have any more slides about that. But as the dimension is growing, it's only the Monte Carlo method which doesn't blow up so badly with the dimension, while this one is depending on the dimension. Okay, so now we go to more advanced method, which is using this U function that I'm trying to integrate, weighted with the probability distribution of K and M. If they are independent from each other, this is just the two probability distribution functions multiplied together. So if this U function is smooth, then I can use this smoothness somehow. And the idea is to write this U response function as some linear combination of basis functions. And now we will use the Lagrange basis functions that you probably know, because you also use it for finite element basis functions. So the Lagrange functions are nodal basis functions, meaning that at a specific point, they take values either 1 or 0. So if I have 3 points, for example, I note it with 1, 2, and 3. The first Lagrangian basis function will be the one which takes value at point 1 and 0 at all the other points. Now, how to formulate such functions, this is really, you should be familiar with it from finite element method, but it's not complicated. You have a general form here, and then you can write, I switched from U to F, and the reason is that now I'm not separating the weighting function from the U, but I say that the product of the two, I call it as F of Q, because now I'm supposing that I don't have two random variables, but I have only one random variable. So let's say it's called Q. And then I want to integrate this function F of Q. This is the function to be integrated. And then if I approximate it with the Lagrange interpolation, then I have here the Lagrange functions that I showed you here. And here I just have to multiply it with the nodal value of f at q1 and the nodal value of f at q2 and the one of at node 3. So this is how I approximate it. And if I use this approximation, then I can write this the integral of f of q by this linear combination. And then as these are just scalar values, I can take them out of the integral term. And what I have here, I get a weight from the integrated version of the Lagrange functions. So now I had an integration rule, and here I use 2 points. So over one element, I write this only, let's say, if this goes from -1 to 1. And then as for a finite element method, you can always map a certain section to a coordinate system which goes from -1 to 1, and then you can use exactly the same rule. And if I use 2 points, so a 2-point rule, then I write a linear approximation of the U function with those head functions, that looks like, just a second, one looks like this and the other one looks like this, where this is 1 and this is 1, and by the linear combination of that 2, I get a linear approximation of f, and I can compute this integral term like that. So the accuracy of this numerical integration with 2 points is n-1. If I have n points, then for example, now I said 2 points, then I have a linear approximation of the function. So I can compute the integral term exactly if this integrand f of q is actually a linear function. So this is the accuracy of the integration rule, which is for 2-point rule, just simply 1, because I can only compute exactly linear functions. Now, if I do a 3-point rule, I have a quadratic approximation, but it turn out that with this type of points, if I choose the points to be in the midpoint and in the 2 boundary points, then the integration accuracy will be not n-1, but n. So if I have 3 points, I can integrate everything, compute all functions, all linear functions computed that are polynomials of maximum degree 3. So it could make you think that maybe, depending on where these points are, I can actually change the accuracy of the integration rule. And because when I set up an integration rule, I need to set up the weights and I need to set up the points. So I have if I have n points, I have 2n degrees of freedom to choose the integration rule. It turns out if I choose in a special way these integration points, then I get higher accuracy. And the best accuracy you can get is 2n-1. So this is the optimal value of an integration rule, that all polynomials up to degree 2n minus 1 can be integrated exactly with n number of points. And such a rule is the Gauss quadrature rule. And I will show you fast proof of why it actually it's true, why I can really compute with d degree accuracy, this integration rule. But here's an example. If I choose the points to be the midpoint rule, so I have only 1 point, but this 1 point, I choose it to be in the center of the element, then it turns out that I have this 2n minus 1 accuracy. So this is the proof that I will only show you in a fast manner. If you want more details, I can send you literature about that. So this is my function u of q, because in the general Gauss quadrature way, the integral term is written with u weighted by some weighting function. So I have this weighting function separated. And if I want to integrate u of q, and I write u of q, let's say u of q is now a polynomial of degree 2n minus 1, okay? So I choose u of q to be a 2n minus 1 degree polynomial. If this is the case, I can write this u of q as this form here, where the psi function is an n degree polynomial, where I have a set of basis functions, actually, psi I, that fulfills orthogonality condition. So these are orthogonal polynomials. I will talk about orthogonal polynomials later on because we will use them for the response surface methods. But you use it also for the integration rule. So if I put here this, the n degree of this set of orthogonal polynomial, then I can write the u of q by dividing u of q by this polynomial. So by dividing it with the polynomial, I get an n minus 1 degree polynomial and a remaining part, which is also maximum n minus 1 degree. So this is also a polynomial of maximum degree n minus 1. And then if I compute the integration, I know that in a general way, I need to use the Lagrangians n minus 1 polynomial. So with the Lagrange function, I have n minus 1 degree polynomial. So when I integrate this term, I have to integrate this rewritten structure of the term, which will be repeated in the next slide. And then what I get, I will need 2 endpoints in general if I don't specify how to choose the points. And then my integration rule is written like that. I can integrate the two terms separately. But if I use this qi to be the 0 points of this n degree polynomial, then this term cancels, and then this whole term cancels. Then the only thing I have is this other part remaining. This part remaining is actually just the integral of the second part, right? But the integral of the second part, here the integrand is only of degree n minus 1. And if this is only of degree n minus 1, it's enough to use n number of points. So this is how I proved if I use a special set of points, and these points are described by those orthogonal polynomials that I generate from creating orthogonal polynomials, knowing that this is my weighting function that I have. Remember, the weighting function is always the probability distribution function that I have. So this is coming from the underlying measure. Depends on what probability distribution function I have here. Then I can create this orthogonal set of basis functions, and I need the nth degree basis function and take it 0 points, and then I will get this 2n minus 1 accuracy. So to sum up, then the Gauss quadrature rule in general has this form that I have a weighting function and the u of q that I want to integrate. And this can be approximated by the values of the u function at certain integration points times the integration weight, where the u of q is approximated with the Lagrangians, with n Lagrangians, and the points are chosen to be the 0 points of this polynomial, and the weights are computed from the integral of the Lagrangian functions. So depending on what weighting functions you have, you will see here different weighting functions. Then the polynomials orthogonal with respect to that are the Legendre, the Jacobi, the Chebyshev, the Laguerre polynomials, and the Hermite polynomials. So these are some weighting functions. Now, this is something like the Gaussian distribution function. That's why when we have Gaussian distribution of the random variables, we use Hermite polynomials for the integration rule. So I search these Hermite polynomials. If I want an n-point rule, I choose the nth degree Hermite polynomial and I check its 0 points, and that will give me the integration point. And for example, for the uniform distribution function, you use these Legendre polynomials. Now here in this table that I have here from Wikipedia, actually, the interval given was from -1 to 1. Now you can also change the interval, but if you have this interval, then the probability distribution function, let me draw here something. So the probability distribution distribution function will be something like that, which goes from -1 to 1, but it has to integrate to 1. So the value here has to be half. So I need a half here. So you have to watch out what weight you have here and how to modify your polynomials if the weighting is different. So this is something that you have to look or take attention to. Pay attention to. Okay, so this is a specific example with the uniform distribution. That's why I have here the half, because the weighting function is just half. And then if I need to integrate this u of q function, weighted by the probability distribution function of q, and now I suppose that this q is a uniformly distributed random variable, which is uniformly distributed bounded by -1 and 1, then this is the term that I have to compute, and this will be its approximation, where I present here an 4-point rule. So the 4-point rule comes from, you see here, if I have uniform distribution, then I need the Legendre polynomials, because the Legendre polynomials are the ones that are orthogonal with respect to a constant function, constant weighting function. And you see up to degree 5 for these Legendre polynomials. Now I need to pick the purple one, which corresponds to the 4th degree polynomial. You see the 4th degree polynomial by purple color, and I take its 0 points, which are the blue points, and this will be my integration point. And if I have the integration points for defining the integration rule, I only need the weights. For example, the weight corresponding to this point here will be the integral of the Lagrangian, which takes value at this point and 0 at all the other values. So I define this Lagrange function, and then I take its integral, which can be computed exactly, and this will be my integration weight. So you will get the weight from this term right here. And now I have the integration rule. I know the weights, I know the points. Then what I have to compute, I just compute the solution or the unknown function u at the integration points, and I multiply it with its weights and sum them all up with the n points. And if I have a 4-point rule, I can integrate everything accurately up to degree 7. So 2n minus 1 is 2 times 4n minus 1 now, which is 7. So if u of q is a polynomial of degree 7, then this is not an approximation, but this is an exact computation. Okay, now what's happening if I have not one random variable, but let's say in our spring example, we had the stiffness and the mass. What's happening then? So then I had a function, which is displacement of the mass at a certain time, which depends on these two random variables. And I have to integrate over them. If they are independent from each other, I can say that here I can use Fubini's theorem. So integrate separately over k and the m dimension. This is the weighting function that I actually explained to you. So both of them has 0.5 value if they are uniformly distributed, but now I take the product of the two because they are independent from each other, so I can just compute the distribution function from the product. And now I have to solve for this integral term. How can I do it? I have the u function, and I can write it as a product of a function of k and a function of m. So I can separate these two variables with this product. And then for u, for this one-dimensional function, I can just write a linear combination with the Lagrangians the way I did, and I take the product with the other one. And then it turns out that what I have here is a 2D rule where the integration rule is just simply summing over the integration points, the solution at the integration points, which are the tensor product of the 1D rules. So if I have a 1-point estimate here, just a second. If I have a 1-point estimate in this direction and a 2-point rule in the other direction, then the tensor product rule will be taking all combination of these coordinates. So in this case, it's only these 2 points. If I would have another point in this direction, I would have another 2 points here and there. Okay, so I can choose different point rules in different directions, and I take the tensor product, so this all combination of those coordinates, and the weights I compute from the product of the univariate weights, of the univariate rules weights. So it's not complicated, but what I have here is the following. If I have the 2-point rule in the m direction, then in this direction I can integrate everything exactly up to degree 3. If I have the 1-point rule in the k direction, I can integrate all polynomials up to degree up to degree 1 exactly. Now if I take the tensor product rule, I can integrate this tensor product exactly. So in this dimension, m to the power 3, I can integrate exactly. In this dimension, k, I can integrate exactly. So with the product rule, also their product can be integrated exactly. So this term here. So the problem with the quadrature rule is that if you, this is just an abstract notation of taking the tensor product of the 1D rules. And what you can see here, how the evaluation times can change with the number of the points, and how the number of the points can blow up if I have different dimension. So if I use, let's say if I have 2 dimension, which I showed you, and if I use in both dimension the 4-point rule, the 2-point rule, then I have 4 number of points. But with the dimension, you can see, so this is always using a 2-point rule 2.1 dimensional rule in all the dimensions, and you can see that with the dimensions how the number of the points blows up. Now, if you have 50 random variables as inputs, and you want to evaluate the mean of the solution, then this is the number of the points you need only with the 2-point rule. This is how many times you will have to solve the deterministic problem. So you need to evaluate the solution at that many number of points. Now you can see that this can take quite some time, and this is something that we probably cannot afford. So in this case, we have two options. One is to not go smart, but go with the brute force approach and do it with random points, with quasi Monte Carlo or Monte Carlo points. And then you can have an estimate of the integral term. And the Monte Carlo integration was exactly invented for this purpose, that they try to solve a really high dimensional integration computation problem. So when the dimension is really high, what you can do is to do it with random points, and then it will give you an estimate. But you can still go a bit smarter when your dimension is not extremely high. And this is the so-called sparse integration rule that Professor Mattis mentioned you, and I will only go through it fast to have a certain idea. So the idea is not to integrate all terms which are in this tensor product exactly, so if I have, for example, a 2-point rule, then I have the linear terms exactly, or sorry, a 1-point rule. I have the linear terms exactly, and the other direction too. So with the full tensor product, I can integrate all of these polynomials and any linear combination of them exactly. Now, the idea, if I only want to go up to degree 1, then let's say I only want to integrate everything which has total degree 1. So I don't want to include this term here. I only want this Pascal triangle that you may have seen already in your finite element background. And this is what for that a solution is to use these sparse integration rules. And the problem is attacked by writing the different degree integration rules with the telescopic sums. So this is the 0-point rule, which is something without any points. It doesn't make sense. So it's just simply a 0. And this is the 1-point rule. And the difference between the two shows how do I get from a 0-point rule to a 1-point rule. So to get to a 1-point rule, I just have the solution times the weight at the 1 point. Now, how do I get from the first point to the second point? Then I have to cancel out the first point, because let's say I have the 1-point rule, which is here, according to Gauss quadrature, but the 2 points will not be that I add another point, but it will be 2 other points, which is located at different points. So then I have to cancel out these points. So I multiply it with the negative weight of the 1D rule, and I multiply these solutions with the weight of the 2-point rule. And this is how I get the differences. This is how I get from 1 point to another one. And then these differences, I can note it as these deltas. And then I write the endpoint rule with these deltas. And this way, I can actually control which terms I want to keep and which terms I want to throw out. And you can see that when you take, it's quite some number of points that you have to multiply it either with negative weights or with positive weights, but there are plenty of terms that just simply falls out. So this way, you actually get smaller number of points, but you can also integrate less number of polynomials, or less degree accuracy. But often you don't want these mixture terms to go for total degree really high. And this is the rule. I'm not going to explain it in more details. I will show you how to use it. But the thing to know is that when your dimension is low, then you can arrive with more number of points with sparse grids, because you take linear combination of different rules. So you need to get to higher dimensions when you use the Gauss quadrature with a sparse grid to get fewer number of points. And I think somewhere the number of points start to decrease from dimension 4. So if you have 4 random of variables, or more than 4 random variables, then you may think about using a sparse grid integration rule. Okay, but as Professor Mattis explained, its stability, because of the negative weights, its stability is questionable. So you really need smooth functions to be able to get an accurate estimation of the integral. And you really have to watch out for that. Okay, so how to do it? And this is the spring. No, sorry, this is only to show how to get integration rule. And this is with already a higher level function. So you can see that I can create not only with these gen-dist functions the distributions, but I can also use an object-oriented way, which is much faster, in my opinion, to define a distribution with mean 5 and variance 1. And then what I need is that if this is the distribution of my k parameter, then this is not a standard distribution. Okay, so the integration rules were usually in the softwares applied such way that they are integrating over a certain standard domain. Okay, if it's Gaussian, then you should have a standard normal Gaussian distribution, meaning with accepted value 0 and variance 1. So in order to go from the distribution or the random variable k to something which has the standard distribution, it's the same way how you do with finite element methods, that this random variable should be mapped to some reference random variable. And this reference random variable has this so-called Bayes distribution. And all the integration rules were applied for these Bayes distributions, okay? That it supposes that your input random variable has this basic distribution. So you need this map, but when you use this object-oriented coding, then I can directly get these maps, which is one of the advantages. So I know that if I have a normal distribution, I should map it to some standard normal Gaussian distribution, and I have it built into this normal distribution that I can get the distribution of the corresponding Bayes distribution that I have the integration rule for. And in this sglib code, I have this polysys character. So for all these different distributions, whether you have uniform, Gaussian, or a beta distribution, I have an underlying Bayes distribution, and I have a corresponding characters. It's a letter, okay? So for Gaussians, the letter is an H, which corresponds to the Hermite polynomials. And you can get this character by asking for the default polysys, okay? Sorry, this is the syscar, and the polysys gives you what polynomials is corresponding to the to this basic distribution. So you have this base distribution, and then you have a default polynomial which is orthogonal with respect to this base distribution, and you have a corresponding letter that you get from this GPC registry function. Okay, it seems a bit complicated when you try out. You see it's not so complicated actually. Okay, so to get this integration rule, I need this letter that I got, which will be for the Gaussian distribution an H letter actually. And now I want a 3-point rule. So by signing that, it will give me the integration points and the integration weights in this direction. And then I can map it back to the value of my real random variable k, where I just need to call this distributions function base to distribution. So the base distribution, I map it back to the original distribution, and then it will give me the integration points of the k parameter directly. Now I can do the same thing with m, with the mass. Okay, I'm not going to show you, it's exactly the same, but with a different distribution. Here I had a uniform distribution. Its base distribution is a uniformly distributed random variable which goes from -1 to 1, and the corresponding letter is p, which corresponds to the notation of the Legendre polynomial, which is orthogonal to the weighting function defined by the distribution function of the base distribution. And I can get the integration points for this direction too. In order to get the tensor product rule, I take there's a tensor mesh function. I think this is in SGLib too, and not an INVIAT MATLAB function. And it will combine you the weights, multiplying them together, and the points. And I think I have a plot of this integration rule. So here you see all the points, and I'm not showing the weights, but you can check it with MATLAB if you would like to. Okay, now this can be done with higher level functions in MATLAB in a much shorter way. If you want to understand in more detail how it's done, you can see it with the previous slide. So I have created, actually, that was my my thing to add it to the SGLib. So there is an object called the sim param set and the sim parameters. So you can define in SGLib sim parameters where you can assign some notation. I call this parameter k, and I call this parameter m, and I put here the distribution that I want to assign to k and the distribution that I want to assign to m. And I add it to this set of parameters, which I call sim param set. So I can add it to this generated empty sim param set. And then I have a set of parameters where I have two parameters, and both of them have different distribution. Now, later on, I will suppose that these two are independent from each other, which most of the case I cannot really suppose, but this time I will. And then the integration rule is directly given by calling the sim param sets get integration points function. I can define different degree rules in the two directions. This is something that I cannot do for sparse grid because it's not implemented there, because with the Gauss quadrature, it's difficult to apply that. With some nested rules, it would be easier, but it's not there yet. And I define whether I want a full tensor or a sparse grid rule here. And then I get directly the values for the k and the m for these generated x integration points. And here you see a plot of the integration points. Now you can do that for as many number of random variables as many you want to. If you have, let's say, 6 random variables, then you do exactly the same thing. You get the weights and you can plot it where I show the plot in two-dimensional plot. So I pair up the different parameters, random variables, P1 and P6 here, and P2 and P6 here. And you see the points are coming from the tensor product rule. Now I can do the same thing, but with the Smoyak integration rule, the sparse integration rule. So the only difference is that here I put grid is Smoyak, and then I can plot this Smoyak integration rule. And because I have here now 6 dimension, for 6 dimension, I can only reduce the number of the points. So here I have 1,495 points, and I don't remember how many here I had 15,600 something points. So you can see that it's not a stable integration rule, but when you have a very smooth function, it may be worth it to try the sparse integration rule because you can significantly reduce the number of the points where you have to evaluate your solution. Okay, let me check the time. Okay, good. So this is the sparse grid. Oops, am I going backwards? Okay, and now I turned over the slides. Now I'm just running through this example. This is the spring example, and this is how to compute direct integration, meaning that I evaluate some statistics. In this case, let's say the mean value and the variance of, I think I only compute here actually the mean value of the solution by approximating the mean operator with the numerical integration. And this is the way to do it. So first of all, you need to define the deterministic solver. If you do a finite element code, then this is a solver which takes as input the some number of random variables and takes as output your quantity of interest that you want to compute the mean of. So now my SOA function is a spring SOA function, which is in sglib. I think if you want to run it in sglib, you have to put it directly to the path because it's not done by the startup function. But if you run into that problem, please write me an email, okay? So it's inside sglib, this spring SOA function. Maybe you have to add it to the path to be able to reach it. And this spring SOA function takes a number of inputs, okay? Usually your inputs are different from only the uncertain random variables. So in this case, I need the initial position of the mass, the initial velocity of the mass, and this is actually the stiffness of the mass, and this is the damping of the spring, and this is the stiffness of the spring, and this is at what snapshot, what time I want to compute the position. So it gives two outputs, actually, the position and the velocity. And sorry, this is mass and this is stiffness. I don't know if I said it right. So it takes all these inputs, but I want to fix those inputs. So I make a function which depends only on k and m. So I create a q vector whose first element is the k and the second element is the m. And now I have this random vector, and I want to compute the mean of the solution due to the uncertainties of this q random vector. And the way to do it, I have to get the integration rule. First, for that, I need to define the distribution of these random variables, the mass and the k. And this I have showed you already. And then you need the integration point. And now I use the full tensor product. And I use here a 7-point integration rule. And so this is nothing new. And then the only new thing here that I have to call for each integration point, I need to evaluate my solve function. Okay, so I have a set of Q points which comes from the integration rule, and I have to call them. And then the way to evaluate the mean is simply collecting the evaluations in this U vector, and then what I need to multiply it with the corresponding weights, and then I get the mean value. And I can also compute the variance in a similar way. Okay, so I did compute the variance. Okay, so now we can compute statistics of the solution, but our final target is something to do the inverse thing, so to do the identification. If we want to do the identification, it's very convenient to make a proxy model, so a response surface approximation that I talked about. And this is somehow a smarter way to attack the problem. And you can use this smarter way to evaluate statistics and also to use it for the inverse method. So this is something that will turn out to be extremely useful to evaluate statistics, sensitivities. Now I'm not going to go into the sensitivity part, but that's also extremely useful, and you can find it in the examples in this website that I showed you. And in order to make a surrogate model or a proxy or a meta model, there are different ways to say it, I need some basis functions. So remember, I want to write my response or a function of my response. So now this function is y. If I don't directly observe u, then I will need rather an approximation of my quantity of interest is a function of u, which I call y. Then y can be written as a linear combination of some basis functions, and these basis functions depend on those random variables. So in the spring example, this would depend on k and m, or actually not directly k and m, but on the mapped reference random variables. So if I have a uniform distribution from 1 to 2, then I map it to something from -1 to 1, and that will be the so-called germ of that polynomial, okay, the reference random variable or the germ that I will use for these basis functions. So this will be functions of the dimensions corresponding to the different random variables. And this will be the coefficients that I want to compute. Now, what kind of functions I can use here? And Professor Mattis told you there are several things that you can use here. You can use neural networks, you can use polynomials, you can use Fourier functions, you can use radial basis functions, whatsoever. So you can have plenty of choices what to do here. And actually, some of the methods are not depending on the polynomials that we will use now, but we will use polynomials and the special type of polynomials, namely the orthogonal polynomials. These are exactly the same polynomials that I mentioned you for the integration rule. So you will need to use the 0 points of these polynomials, right? And I say they are orthogonal when this condition is fulfilled. So when I have these stochastic computations in this probabilistic setup, then I need to define an inner product. And Professor Mattis explained you that the expectation of the product of two random variables can be defined as an inner product, okay? So the only difference from the, maybe you met already in the functional space how to define an inner product, but the only difference here that it's weighted by this weighting function, okay? You don't take just product of two functions and integrate it, but here you weight it with the probability distribution function of psi, which is now the germ of the expansion. So then this condition has to be satisfied that this integral term or the inner product of the two basis functions is just simply the Kronecker delta times the norms of the polynomials. Okay, this is the norm of the polynomial, and and this condition you should satisfy. Now, if you have this special type of polynomials, these orthogonal polynomials, there can be different types of polynomials. It depends always on the underlying probability measure. If you have Gaussian random variables, then you use here the Hermite polynomials. So these ones will be the Hermite polynomials. If you have here a uniform distribution of the psi, then this will be the probability distribution corresponding to the uniform distribution. And here you will have the Lejeune polynomials, okay? And then they will satisfy this condition. Now, if I use this special type of polynomials, then the statistics can be quite easily computed. So I write this as a linear combination of the coefficients and the polynomials, and this I can write in a matrix form, which I show you. Unfortunately, I only have the mouse, so it's quite difficult to write, to draw this, but I give a try, okay? I have here a matrix, okay? And I have here another matrix that I multiply together. So I have here the basis functions. If I have Gaussians, then I have here the Hermite polynomials. This is the 0-degree polynomial, H0. And here I have, let's say, H1, the first-degree Hermite polynomial. And here I have the second-degree polynomial, H2. Okay, this will be the psi m vector. And let's say if I have one response, this is only one row. And here I have the coefficients corresponding to the polynomial. Now this will be this nu 0, the nu 1, and the nu 2. I think you can imagine, okay? So I will multiply this with the second-degree polynomial, this with the first-degree polynomial, and so on. So this will be the expansion of the position of the mass. If I also want to, if I have two outputs, or if y is really a vector and not a scalar value, let's say because I have in this the position of the mass and the velocity of the mass, then I have here another set of coefficients that I write in the second row. And then I can write this expansion in this form. So how do I compute the statistics? I can really easily compute it by taking the expected value and using orthogonality condition. If I multiply it with 1, which is always the 0-degree function that I have, then I have here, I can put here an extra phi 0, and the expected value of phi 0 and phi I is just simply the zeros coefficient. So this will here, this corresponding, sorry, just a second. So this that I multiply with the 0-degree polynomial will give me directly the mean value of the position. And this, what I will have here, will give me directly the mean value of the velocity. So this column of the coefficients will correspond to the mean values. And then the covariance, you can also just simply compute it from the coefficient, from product of the coefficients and the rest of the coefficients. So you have to get rid of the zeros one, which corresponds to the mean value, and you leave the rest. So if you put here zeros instead of the values here, then you have the fluctuating part of the random vector, and this fluctuating part of the random variable. And if you take products of those coefficients, you can get the covariance matrix. So these are really cheap evaluations. You can compute them really easily. Now, let me check the time again. Okay, I wrote down that I have time until 1:10, right? So I have a half an hour more. Okay, so I will rush up. How do I generate these polynomials? Now, the generation can be done by the Gram-Schmidt orthogonalization. If you're not familiar with the Gram-Schmidt orthogonalization, I'm sure you know it in the Euclidean space. If you have 3 vectors, for example, here I have a v1, v2, v3 vector. If you want to orthogonalize them, the way to do it is that you choose, for example, the first one to be v1. So this will be my q1, and you can normalize it if you wish to. And then you take the second vector v2 and you project it onto q1, and you subtract this projected part, and what you get is, you see here a 2D image of that. So if this is v1, you project this v2 vector onto the v2, and you subtract this part. What you get is directly this vector. So then you get this q2 blue vector. Now you have a third vector, and then you project it to both of the already existing bases, so to q1 and to q2, and subtract both of the projected part, and then you get the rest, which will be this vertical vector q3. So when you are in the functional space and not in the Euclidean space, you do something similar to that. You start with, now the v1, v2, v3 will be directly the monomials. So 1 psi1 squared psi1 to the power 3. These are the monomials. But these are not orthogonal with respect to the underlying, let's say, Gaussian measure, if I have a Gaussian measure. So I want to orthogonalize them. So I do it exactly the same way how I do it with the in the Euclidean space. The only difference is that what defines orthogonality in the functional space is now my expectation of the product of the two functions. So this is how I define this inner product, and the inner product defines what does it mean orthogonal, okay? And if I have this inner product, then I can write this, the projected part, as expected value of psi1 times my first basis function, which I choose to be the first constant term here. And then I can project it onto that. And I have to subtract this projected part from the psi1, and then I get my next basis functions. So this is how to do it, and you can do it by hand to get these Hermite polynomials, Legendre polynomials, Jacobi polynomials, and so on. Or you can Google Wikipedia and you find how these polynomials actually look like. Okay, but I show you the ones for the Hermite polynomials, and this is actually the practical way to do it. Now in SJLib, you don't do directly the Gram-Schmidt orthogonalization, but you use the so-called recurrence formula. If you start with a 0 function and the 1 function, so this is the -1th term and the 0th term, then you can get in a recurrence way the next term h1 from this formula, where the A, B, and C terms are given for any type of probability or weighting function that you have, which is defined by the density function. So now if I have Gaussian random variable, then I have this exponential weighting function, which is the probability density function of the Gaussian random variable. And you can find in this Gauch, I can give you the exact reference of this Gauch's book, but you can also find it in the literature that I will send you and share with you. You can find that for a specific weighting function, what are those A, B, C terms, and for Gaussian, this is just 1, 0, and n, and then you get as many number of Hermite functions as many you need. Okay, so this is how I get my orthogonal basis for approximating the solution. But now, what do I do if I don't have only one dimension, but higher dimension? So here I show you a two-dimensional problem. And in two dimension, you can also define a set of basis functions. So here, this is the linear index of the basis function. I have 9 basis functions for this example. And I have two dimensions. Let's say the first one corresponds to k and the second one corresponds to m. But here I use the Hermite polynomial, so let's suppose they are Gaussian, which they cannot be actually because they are stiffness and mass values. They cannot take negative values. So you should use a bounded distribution for that. But let's suppose they are Gaussian. If they are Gaussian, then I use the Hermite polynomials, but I have two variables now, one corresponding to k and the other one corresponding to m. And the way to do it is that you can show that when you take any products of these one-dimensional orthogonal polynomials, then the product will be also orthogonal. So this is really nice. And then you can take the products of the univariate basis functions. And which product you're taking is defined by the so-called multi-index. This is what Professor Mattis also mentioned you, I believe. So this shows you that I'm taking the product of the Hermite polynomial in the first dimension of 0 degree here, and in this, the second dimension, the Hermite polynomial of the second dimension, I take the 0th polynomial too, and I take the product of these two. So this will be the product of h0 of xi1 times the h0 of xi2. So these are the multi-indices that you see here in these indices, okay? And the way I construct a set of basis function is such way that the total degree of this polynomial is, let's say, less than 3. So these values should sum up to 3 or less than 3. So you see that this is the constant term, this will be a linear term and another linear term, and so on, okay? Here you multiply the third degree polynomial with the 0 degree polynomial, etc. And this is how a multivariate orthogonal polynomial set is created. Okay, now how do I do the orthogonal projection? So now I make the surrogate model, which means I want to have this approximation of the y as a linear combination of those orthogonal polynomials. And I want to get the coefficients. How do I get the coefficients? I get the coefficients such way that I want to minimize the expectation of the squared error, okay? What is the expected value of the squared error? This is actually a norm. This is why I wrote it like that. If I define the inner product to be what I explained how I define the inner product to be, then the norm that is induced from this inner product is the expected value of the squared function, right? So this is just simply the norm of the error. This is what I use here because I can connect this by the nice theorem that if I have a certain inner product and I induce a norm for that, then this norm can be minimized when the error is orthogonal to the approximating subspace, okay? So this is only true if the orthogonality here is defined by the inner product from which I derive this norm. So this derived norm will be minimized, okay? So if the error is orthogonal to the approximating subspace, then I will have this minimized, okay? Good. Now I can write this down. What does it mean? Or what does it mean orthogonal to the subspace? So it means that to any element of the subspace. And now the subspace means that all those elements that can be written as linear combination of those orthogonal polynomials. If I write all functions, all possible functions I can write as linear combination of those, then I can just show the orthogonality to all the basis functions, and then any element which is written with a linear combination will be orthogonal to that. So using this approximation, the GPC expansion here, I can show orthogonality is computed from orthogonally projecting to the so that the coefficient corresponding to the ith polynomial is just the projected part of y which is projected onto this phi I term. So how to compute the ith coefficient? I take the basis function, I take the product with the response or the quantity of interest, and then I integrate it weighting by the probability distribution of the underlying probability measure and dividing it by the polynomial, the norm of the polynomial. So this is how I compute it. But the problem is that this is an integral term which depends on a function that I already said that I cannot explicitly write, right? This comes from a finite element analysis, let's say. So this is something that I do not have, right? The whole aim of the thing is to write an expansion like that to be able to describe this dependence. Okay, so this is somehow strange that I want to know what is this, and for that I need to compute this integral where I have this term that I don't know what it is. Okay, but as I said, an integration can be approximated with a numerical integration. So if you can compute this y at certain points, and in this case I want to compute them in the integration points, then I need to evaluate this whole term at those integration points and use the corresponding integration weight, and this way I can just simply compute the coefficient. Okay, and this is the steps that I have to do in order to do that. And you see that this term, the coefficient, is computed from an approximation which is coming from an integration rule. Okay, so what you need to do, you need to define the solver, you need to define the basis functions that you will use, compute the norms of the basis functions, and get the integration rule, and then evaluate at the integration points your quantity of interest, and you also need to evaluate the basis functions at the integration points, and then you can directly compute the coefficients. And you see here the code that's doing the job, defining the solver, the distribution of the random variables, and maybe I will only stop here how I define the basis. So this is how to define the basis in SGLib. And now I'm really left behind in time. So this is how I define the basis in SGLib. I can just simply do it by writing with the sim-param set that I defined. I can directly write getGerm, which means it will give me a basis, a so-called GPC basis, and a GPC basis in SGLib is treated in the following way. It's actually a cell in MATLAB, and so the V equals to a cell which has two elements. The first element is a set of letters depending on how many random variables you have. Now I have two random variables, and I do not know now what I defined. I think I defined uniform distribution for both of them. So I have two P letters, which tells me that now I need the Lejeune polynomials. So this is the character defining the underlying reference random variable. And I have also a second element, which gives me a vector with the multi-index set, okay, that I showed you before. And it will be empty when you just say get a germ, because I didn't define any degree, how many degree of approximation I want to have. So I will need, I can only set this multi-index set. Now I show you just to remind you that this is this matrix, which is right here. And if I would say modify it such way to have degree 3 approximation, then this will be the matrix that you get as a second element of the basis. Okay, so this is empty now, and now I need to define what degree of approximation I want to have. And here I need a really high degree approximation because I have all this oscillation that you saw in the response surface that now I want to approximate. So I put here now 12, so it will have quite a number of rows here and 2 columns that corresponds to the k and the m parameters there. And this way I just define the basis in archlib. And now I can just get with this function its norm. I can get the integration points, define that I want a full tensor grid now because I have 2 dimension. It doesn't, it's not worth to use a higher degree approximation. And the way to compute with orthogonal projection, the functions you can see here, you can check it on this website that I give you. So I'm not going to show you point by point, but with the help of that, you can evaluate mean value of the solution, the sensitivities that I'm not going to talk about now, and the variances. And this is just corresponding to the Sobol sensitivities. So this is all I leave out now. And you can also plot the response surface. If I only have 2 dimensions, I can evaluate at any mesh points the solution. Now for any value of k and m, I have a response. And the crosses are where the integration points were. So these are the points where I have actually computed the solution, and the rest is computed from the expansion. Okay, so now there are other ways to compute it. And what is interpolation? And the interpolation is really easy to compute. Maybe I'm not going to explain now. The only thing that when you do integration in 1 dimension, if you have, let's say, some response like that, and if you have, let's say, 2 points here and here that you computed, then an integration will be an approximation. So, sorry, when you compute the coefficients with the interpolation, then what you will do is that you will get a function that goes through those points, okay? So you want that at the interpolation points, Q1, Q2, and Qm, the expansion will be exactly the solution that you computed. So maybe it will look like something like that. Oh, it has to go through here, okay? Something like that, maybe. Maybe not, but as you increase the number of the point, the exactness will increase. Now it depends how many degree of approximation you want to have, but this is a matrix, okay? I'm sure you can see how this can be written in a matrix form, and it's a well-defined set of equations. If you have as many number of points, as many number of basis functions you have. Now, if the number of the basis function is less, then you have more points, and you cannot make exactly your approximation to go through these points, but you can minimize the in a mean squared the deviations from those points. And then we talk about regression in MATLAB. You exactly carry out the computation exactly the same way. And this is the important slide here, that when you do interpolation, then what you can do is that though your approximation will go through your function that you want to approximate, but in between the points, you never know what you actually do. And there's a phenomenon which is termed as Runge's phenomenon, that when you increase the number of the points, you can increase these oscillations on the boundaries. And this happens mainly if you use equidistant points. Please remember that in numeric, equidistant points are never really good for approximation. So a good set of points to use for the interpolation is, for example, the Gauss quadrature points that we use for integration. Exactly the same points can be used also for interpolation because they have the nice properties that there are more points on the boundary than in the middle part. So this is something that you have to look for, and these are the slides for regression and interpolation. And now I'm going to switch to the other presentation. This one. Okay, which is random fields. I have 5 minutes to talk about the random fields, which is not much, but I will rush up and maybe I will finish this part next time, but hopefully I can get to the main things. Okay, so the motivation for that is this example that I showed you already, that in the Adriatic Sea there is this gas platform, and the seabed is actually moving downwards because of sucking out gas. And the problem here was that they had a computation, a finite element computation, with this set of equations. So this is the boundary value problem that you have here, the strong form of the equation. And the problem was that their prognosis for the displacements were way smaller than the ones that the experiments showed. And the idea was that this is the way to formulate the equation that I will shortly talk about. But everything depends on the constitutive model, and the constitutive model depends on the compressibility. And the compressibility was taken to be this term here. So it depends on the effective stress. So that's why it's a nonlinear problem, because the constitutive model depends on the actual state of the gas reservoir. So if I can compute this effective stress, then there is a power law which gives an estimation of how the compressibility is described. And this is just a number which is not far away from 1. So this is just a little bit nonlinear. But the problem was that this lambda value and this CM0 coefficient was estimated from measurements. They drilled into the soil and they made some measurements. But the problem was that these measurements were not done at the place in situ, okay? But they were done with similar experiments. So then they found out that probably this compressibility is wrong, and this is what they have to modify, and this is what they have to update. So in the next tutorial that I give tomorrow, and on this one, I will talk about how to actually do this. Okay, so these are some basics of random vectors, and I'm not going to go through that because I don't have the time. These are the prerequisites, how you define marginal density and covariance. Something that's important to note that when I have several random variables, because, for example, I have different compressibility values at different mesh value, then there are not just random variables that can be defined at a certain point, but there's a covariance function which also describes this random vector, which you cannot ignore. Now, if the covariance matrix, so this is a matrix, in the diagonal, you have the variances at the certain of the elements of the random vector, and in the diagonal you have the covariances. If the covariances are 0, I say that they are uncorrelated random variables. But it's important to say that when they are uncorrelated, it doesn't mean that they don't depend on each other. And when I divide the covariance matrix with the standard deviation, I get the correlation matrix, which has ones in the diagonal and some values in the off diagonals. And the off diagonals are showing how much correlated are the different pairs of random variables. So you can see that this doesn't mean that if it's 0, then they don't depend on each other. You can see that there are some different set of sample points from two random variables, and you can see a clear dependence here where the correlation is 0, okay? So you can get this clear dependence, but still get a 0 correlation. And you have to know that when they are uncorrelated, it doesn't mean that they are independent from each other. If they are Gaussian and uncorrelated, they mean that then you can know that they are independent from each other. Okay, so this is the finite element problem that I have. These are the set of equations. When I write the weak form, I can derive it to this nonlinear set of equations that depends on the nodal displacements A and the nodal pressure terms P. And I can solve this nonlinear set of equations by the Newton method, where I have here the tangent stiffness matrix and the change of the nodal displacements and this function at the actual point. So this is the linearization of the problem, and in this case, our uncertainty came from the stiffness matrix. The stiffness matrix is computed from this integral where these are matrices. The B is the known finite element matrix with the derivatives of the finite element basis functions, and the C is the constitutive matrix. And the constitutive matrix is shown here with the Poisson numbers that you see here and scaled by the inverse of the compressibility. So this was the constant that was the uncertain either random variable or random field for me. So if I suppose that at all the mesh points this compressibility is the same, then this is just one random variable. If I suppose that it can change throughout the spatial domain, then this is a random field. And now I show you what happens when I have a random field here, okay? So this is the CM, that was described like that. And to take into account my uncertainty, I scale it with this FCM scaling. So this will be my random variable that scales the compressibility, the original compressibility. Because I'm uncertain about whether it's magnified or not magnified. Just as a comment, I should also treat as a random field this lambda value probably, because that can also change if my soil is inhomogeneous, but that's another issue. And now I run out with 2 minutes and I need 8 minutes, okay, to finish. So this is the general framework of the deterministic problem that I have. It takes this scaling field of the compressibility field. I need to evaluate it at the certain finite element for the certain finite elements for each value, and then I can compute with the deterministic finite element solver the nodal displacements. From the nodal displacements, I can compute the whole displacement field, but now I only need the displacement at certain values where I can actually observe the displacement. So that will be y, which will be taking only the vertical displacement at certain nodes. And this will be my quantity of interest. So the vertical displacement at the observation points. And this will be my black box solver, okay, that I will use for the analysis. To change it to a probabilistic setup, I will modify the description of the scaling factor. Now this is a capital letter, the scaling factor, because now it is a random field, okay? It depends on the x, y spatial variables, and it depends on the actual realization, okay? So now I suppose some prior distribution. So I don't know exactly what is this, but I try to reflect my uncertainty with the probability distribution function. And this probability distribution function will be a log normal field. It will be log normal because I know that the compressibility cannot be scaled with a negative number. So I really have to look out for that, as Professor Mattis explained. If you choose elements from the constitutive matrix, you also have to watch out that it stays positive definite. So you have to choose your random variable such way to assure that these properties that comes from physical assumptions, they are satisfied. So that's why I'm choosing a log normal distribution function with some mean and sigma. These are the values that I used for the analysis. And this is not enough to say that I have some distribution function at a certain nodal values, but I also have a covariance, how these different points depend on each other. So the covariance shows me how much two distinguished points, are changing together or separately independently from each other. Okay. Now, if my compressibility field is a really smooth function, then these values are strongly correlated. If it's more like a white noise, then there's no correlation at all, and they are completely independent from each other. Now, it makes sense that for a soil, it should be somehow very similar to each other. It should be somehow a smooth surface, the compressibility field. And this is something that the geotechnicians usually tell you, what is the covariance. And the covariance can be given by a covariance function, which Professor Mattis also mentioned you. I used here the Matern covariance function. You can use Gaussian or exponential covariance function too. So this describes what will be the correlation in between the two random variables. And it only depends on the distance in between the points. And it also depends on some correlation length and this new value, which gives you how smooth functions you will get. So I fixed the new value to a value of 2, which is somewhere in between, a bit more rougher than a Gaussian covariance function. And I had a quite large covariance correlation length, which gives you a quite smooth functions. Okay, so this is how I define my prior probability distribution, which reflects my knowledge about what I know about this scaling factor. And then the probability distribution function will look like this. And here in the exponential, you have a Gaussian random variable. Okay, and now this Gaussian random variable is a Gaussian, it's not a random variable, it's a Gaussian field. Now this Gaussian field, I don't know what to do with it because it's infinite dimensional. It depends on the spatial variables and it depends on the actual realization. So what I will do, I will use the so-called Carhun and Löwe expansion to map these theta values to a set of random variables, independent random variables Q. And this I can do with the so-called Carhun and Löwe expansion. So I can have a map which gives me a set of Gaussian independent random variables and a finite number of them if I truncate the expansion. And then I can write this spatial function as a linear combination of some spatial functions and random variables. And this is really desirable because from now on, my task to do the uncertainty quantification is exactly the same how it was. If I involve L number of random variables, I have this L number of inputs that will be the input of the deterministic problem. I can map it to the actual value of the scaling factor by evaluating this linear combination and take the exponential of it. And then the analysis is done exactly the same way. And the example to how to compute it and how I will do it, I will show you tomorrow, okay? Together with the updates. Okay, so that was my part, and I close here, and I'm sorry for making it 10 minutes longer than what I was supposed to. And we will do the identification and the end of the Karhunen-Löwe expansion tomorrow.